It seems like he used a lot of information about real-world applications, which aren't really in Dr. Cosper's notes. Sometimes they are, but sometimes they aren't. So I figured one thing that we could do would be to go through Dr. Cosper's notes, get a general idea of the information, but then go into Dr. Fred's lecture notes and talk about some real-world applications, just because it seems like those are more and more of the questions on his quizzes. Okay, what are heterocycles?
They're like cyclic things with nitrogen, oxygen, phosphorus.
So a general way of describing them would be cycloalkanes, but one of the members is the carbons is replaced by a different atom. So you mentioned nitrogen, oxygen. What was the third one?
Sulfur and phosphorus.
Okay. You probably won't see many, if any, phosphorus ones for this chapter. I don't think he usually brings those in. But so, for example, okay, so in terms of naming these, did he talk about that in class? How would we name this one, for example? Good. So you name the cycloalkane. And oxa, what's the prefix for nitrogen? Nitrogen is aza. And then sulfur is thia. Or thi. Looks like he. Some of these, I guess it was just that one. Yeah, thia. Okay. These are UPAC naming. I don't think you're going to have to worry about common naming. There are some aromatic heterocycles that were mentioned by like common name, but I don't know if you're going to need to know them, but we'll go over them just so you have a picture of them in your mind. So it may be helpful to review the chapter, was it from the beginning of this, where we talked about aromatic structures? I can't think of the number, what number that was.
15?
No. Sounds something like that?
Yeah.
Okay.
For
Anyways,
yeah.
you'll see these in that chapter as well, and it might be helpful just to review what makes something aromatic. I know he probably talked about Huckel's rule in this chapter, so again, I would take some time to review that. But these two do get brought up a lot, especially in this chapter. So we have furan and pyrrole. And essentially what we have here, the reason these are aromatic, so when we think of benzene, the thing that makes benzene aromatic is the fact that you have electron delocalization, okay? So you have basically a system of pi orbitals that allow for electron movement around the ring, okay? So this system of pi orbitals is necessary for something to be considered aromatic. So these are aromatic because we again have this pi system. The reason that it looks different is because we don't have necessarily an alternating double single bond here. But these electrons in nitrogen are in a pi system. So it connects these other pi orbitals, okay? So even though it looks slightly different, the same mechanism is happening here. It's just, it looks a little bit different because we have an oxygen instead of a double bond. Does that concept make sense? Okay. What is Huckel's rule?
4n plus 2.
Exactly. So 4n plus 2. And what is that referring to?
Pi electrons.
Right, so the number of pi electrons necessary for something to be considered aromatic. So if we were to, so the different, so if we had 1 pi electron, what would our Huckel's rule number be?
6.
We had 2,
10,
3,
14.
and you probably won't have more than that, but. So then the key is finding out how many pi electrons are in an actual molecule. This part is easy. This part is more difficult. How many pi electrons do we have in furan?
Eight. 5? No.
10.
Any other guesses? It's actually 6. And this is why it's the hardest part. So let's talk about it. So the double bonds are the easy part, right? When we see double bonds, we know that how many pi electrons are in a double bond?
2.
2. So every double bond is 2 pi electrons. So we automatically know that there are 4 pi electrons here. The hidden pi electrons are these ones, okay? And I know it's tempting to say that all 4 of these electrons, especially the way that I drew it, so I apologize for that. But actually there's only 2 of these electrons that are in this pi system. These 2 are actually in a different pi system, which is at a different, it's on a different plane. So we're only looking at the vertical ones because those are the ones that link up to make our delocalized pi system. So we have 2, 4, 6. Which is why this one is an aromatic.
What does n mean again? When you're looking at
So that just refers, this is the confusing part. Just know that you're looking for something that matches these numbers. N doesn't stand for anything, it's just an integer. And that's the annoying part. We want to say that it means, 1 pi electron, right? But that's not what we're talking about here. This just gives you the number of pi electrons that you're looking for. So you're not actually finding a number and then plugging it in here. That's not what's happening. It's annoying. I feel your pain.
Okay.
So this formula is only used to get a set of numbers. The number, the n that you're plugging in there, doesn't actually stand for anything other than a number. Okay? So the number that gets spit out, that's the number that matters. That's the number that you're looking for within these molecules in terms of pi electrons. We can revisit it again because this was probably one of the most frustrating things that I remember from Organic 2. Let's look at a slightly different structure. How many pi electrons? 10. Aromatic. Okay? So these are just some examples. There are a lot more examples in whatever chapter that was, chapter 15. Okay?
So for nitrogen, if he draws it out like that, is he going to add the lone electrons to it?
Probably not. But in this case, you don't have lone electrons.
Yeah, I know.
Yeah.
But for the ones like that, they do.
Mm-hmm. I can't say for sure. He may or he may not. He would draw the the hydrogen, if it was bonded to the nitrogen. So that can be helpful. Unfortunately, that's about as good as we get.
How is there a pi electron cloud with the H?
So The electrons themselves are what in there. This is also bonded to a hydrogen, but that hydrogen is on a different plane.
Oh, okay.
Sorry, I know the 2D drawing is not ideal for a lot of this. If we have some extra time, we can definitely go back to that chapter. I would just have to go get the notes. I didn't bring those today. I should have. But I'm sure they're upstairs. We can do some more examples of identifying pi electrons if you want. Okay, so reactions. So essentially what we have here, I'll draw it just so you can see it, and then we'll talk about the name, because he may just use the name. Okay, so these are referred to as heterocyclopentadienes. Okay, kind of a long, scary name, but essentially, penta is referring to the 5-membered. It's going to be a 5-membered ring. Diene is going to refer to. Sorry, I'm out of order here. Let's look at the final product. So essentially what's going to happen here, when this ring is closing, the electrons are going to shift. Okay, so that's why we have these electrons moving into this double bond. That's why this final product is referred to as a diene. Penta is referring to the member of rings in the system, and it's going to be some type of heterocycle. Now, I believe in his notes, he just has it as an X, which is slightly confusing. Really, that X is referring to either a nitrogen, an oxygen, or a sulfur. So one of these oxygens could potentially stay, or depending on what reagent we use, we could substitute that for a sulfur or a nitrogen.
So
Sorry. No, it's okay.
If the reagent contains like a sulfur or a nitrogen, that's what's gonna.
Yeah, so you could substitute it with, I don't know exactly what type of reagent they would use for this specific one, but yes, that's where that substitution would come from.
Even though there's the 2 oxygens on the beginning
So
portion.
you could end up with an oxygen, but you could substitute that for something different if that's what the final product wanted to be, if you wanted that to be it.
Why is it NR?
So nitrogen, because of the bonding, and I'm assuming it's either going to be nitrogen hydrogen, because nitrogen wants 3 bonds, or it could be an amine that's being added, something like that.
Okay. So is the heterocyclopentadiene the starting product or that?
Sorry, ending product.
Okay.
Got ahead of myself.
So you start with a dicarbonyl compound? That's what that is?
Yes.
Do you always start with the dicarbonyl?
Yes, because yes, you need the double bond. I suppose that in this case it's a ketone, but it doesn't necessarily always have to be a ketone. But it does have to have 2 carbonyl groups. All really good questions. Anything else for this one? Okay. This example is for pyrrole, but technically this could be any heterocycle pentadiene. So this could also be an oxygen base or a sulfur base. And really what we're talking about here is EAS. What does EAS stand for?
Electrophilic aromatic substitution.
Perfect. Nice echo, guys. So for this one, really what you need to know this should be a positive charge. Does anybody see the electrophile in Dr. Cosper's notes have a negative next to it?
Yeah.
Okay, that's a typo. Really you need to know where the substitution is occurring. So when you are numbering any of these heterocycles, remember that the heteroatom, whatever isn't carbon, is your number 1. Okay, so you're going to number it based off of that. So in an EAS, you can have substitution at 2 different places. So really you want to know that 2,5 numbering, where that's going to happen. And your final product, again, it's just a substitution. So let's say that we have your electrophile added here. All you're removing is a hydrogen. So hydrogen is being removed. You're substituting that hydrogen in for that electrophile. In terms of reactivity, I'm not going to do the names because I think it's just easier to think of it this way. So a nitrogen heterocycle pentadiene is considered the most reactive. Benzene, something that's not a heterocycle, is considered the least reactive, and we're like, this is really, really far down on the list. Okay, so a heterocycle is really required to make this reaction happen. Okay, so nitrogen, so our pyrrole is considered the most reactive, furan below that, and then sulfur base below that, which is thiophene. So I would just know the heterocycle order in terms of reactivity. So carbons 2 or 5 are where this reaction usually takes place. Pyrrole is the most reactive. We okay with this one? I'm actually going to keep this up. The next one is protonation. So instead of adding an electrophile, we're adding an additional hydrogen. So remember, we already have a hydrogen coming off of each of these. So we're adding an additional hydrogen to that instead of replacing it. So if we were to, the site of reaction isn't going to change. It's either going to be on carbons 2 or carbon 5. But if we add it to carbon 2, adding that additional hydrogen is going to cause a shift of electrons. We can't keep the double bonds where they are because our carbons have too many bonds. So essentially what's going to happen we're going to get movement. So this double bond is going to move here. This one's going to move here. This hydrogen is going to be removed. And overall, we're going to have a positive charge here. So protonation of pyrrole. Same places, we're looking at carbon 2 or carbon 5. A shift of electrons is going to occur. I don't think that he would make you draw it, but just know that you have to offset that positive charge now. And so your nitrogen is going to end up having a positive charge. It should also be noted that for this to happen, you need a very strong acid.
What's the pKa note on the side of Dr. Cosper's notes? The 4.4?
Mm-hmm.
It means it's more acidic than, or more, less acidic?
So that pKa is just giving you an idea of how strong of an acid that is. So essentially, we're reacting this, if we're reacting this with a strong acid, okay, that would mean that this is the base in this reaction, right?
Mm-hmm.
So our final product, which is this, is going to be the, oh my goodness, what's it called? Oh my goodness. Conjugate. Conjugate acid. So that's just there to give you a relative idea of how strong that conjugate acid is. You're not really relating it directly to your starting product because that's a base. Or is acting as a base, I should say. So opposite of protonation, you can also deprotonate pyrrole. This happens much more readily. And you're not deprotonating from the carbons, you're going to deprotonate the nitrogen. So when that happens, so we react this with a base. Okay. Essentially, you have a very negative electron-rich ring here. This final product is considered very stable. You can see there's kind of an interesting drawing. I'll recreate it up here. It kind of looks almost like benzene. Essentially, this is just showing, additional electron delocalization. Basically, you have this very electron-rich ring, and resonance is stabilizing this form, which is why deprotonation is much easier to do when you're talking about pyrrole than protonation. So let's kind of review these last three. So electrophilic aromatic substitution. You're going to be reacting with a heterocycle pentadiene, could be any of the three that we talked about. You're reacting on carbons 2 and 5. There's going to be a substitution. Pyrrole is the most reactive out of the three that we've talked about. Protonation of pyrrole can happen with a strong acid. Same sites of reaction, carbons 2 and 5. Deprotonation is much easier to do than protonation, and that's because the final product is highly stabilized by resonance. We good on those three? So, going back to EAS, but now we're going to talk about Ppyridine. So here's our Ppyridine. We did have this, something similar to this one up before. this doesn't usually undergo EAS. Dr. Cosper notes makes a point to say only under extreme conditions. And this is really because this ring is considered electron poor. Again, I would know where substitution could happen here. So if we're looking at the nitrogen, oops, I did that wrong, sorry. 1, 2, 3, 4, 5, 6. So carbons 3 and 5 are where we're going to see an attack happening. And again, we're substituting our electrophile for a hydrogen. So pyrrole, 2 or any of the pentadienes, 2 and 5, pyridine, 3 and 5. Okay.
Pyridine is a pentadiene?
No. So when we were talking about the pentadiene, so pyrrole, furan, that was 2 and 5. Pyridine is not a pentadiene. It is a heterocycle. Don't worry about it, because you can't. So it'd be hexa because it's 6-membered,
Yeah.
and would be triene. But I haven't really seen him use that in, like, they don't really use that phrase in the literature. So
Okay.
it's not the same as your furan or pyrrole. It's a different aromatic heterocycle. Good question, though. So there really haven't been that many details on this reaction. The one that I have seen more questions on in the past, get rid of this. The Chichi-Bobbin reaction.
He loves that one.
Mm-hmm.
I think he just likes to say it, if we're being honest. So we just talked about electrophilic aromatic substitution. Pyridine doesn't do that very well. Nucleophilic aromatic substitution, which is what the Chichi-Bobbin is, undergoes it very readily. And again, that makes sense. We just talked about how this ring is considered electron poor. So why would an electrophile be attracted to it, right? So that makes sense. Here we have a nucleophile, which it itself has a negative charge. So it is going to be much more attracted to this electron poor ring. So for both of these two reactions, you should know whether it's going to react or how well it's going to react and why. Okay? With this one, you also need to know where substitutions could take place. So we're looking at carbon 2, 4, or 6 here.
Just the even number of one.
Just the even number of ones. So pyridine does not undergo electrophilic aromatic substitution very well, only under extreme conditions. And that's due to the electron poor ring. On the other hand, the Chichi-Bobbin reaction or nucleophilic aromatic substitution undergoes very readily. Nucleophiles will attack at either the 2, 4, or 6 carbon.
Is that because of activation or deactivation of the ring? Or is that not involved?
You can't think of it in that terms, unfortunately, because when we're talking about that, we're talking about a substitution on the ring that's affecting it.
Okay.
This nitrogen is part of the ring, so it's slightly different.
Okay.
Okay. So we're going to shift a little bit, and we're going to be talking about some multi-ring systems now. Okay, we're still going to be talking about EAS and NAS. So quinoline is essentially a benzene attached to a pyridine. I don't think he'll make you draw it, but you should have an idea when he's talking about quinoline, this is what he's referring to. So we have two rings fused together. Now the tricky part with this, we talked about the fact that pyridine is electron poor, right? We know that. However, we should also know that benzene, on the other hand, is considered electron rich. So when we're talking about electrophilic and nucleophilic aromatic substitution, these rings are going to react differently. Isoquinoline is very similar, we just have a slightly different orientation of the nitrogen. So almost identical, just a slight shift, still making the ring electron poor. So if you remember what we just talked about when we were looking at specifically pyridine, a lot of this is going to directly apply. So I'm going to use a different color. Okay. So electrophilic aromatic substitution doesn't change regardless of whether we're talking about quinoline or isoquinoline, because that's going to be attacking the benzene ring. Electrophiles are going to be attracted to the electron-rich ring. So those numbers or those sites are not going to change. I think this would be a pretty easy question for him to ask you, and you just have to draw arrows. Okay? So the carbons on either side of that benzene ring, that's where electrophilic aromatic substitution is going to happen. When we're talking about nucleophilic aromatic substitution, it's whatever carbon is connected to the nitrogen. Okay? Is there anything else that you remember him talking about when we're talking about quinoline or isoquinoline? Does this kind of look like what he talked about ish? Okay. Okay. So then he has some different facts. So let's talk about those. So there are some drawings. I don't think that with these ones he's going to have you draw anything. But there is a 2-ring fuse system that contains nitrogen, and it's referred to as indole. The reason that he's bringing this up is indole is part of the side chain of tryptophan, which is an amino acid. So he could ask you, what nitrogen-containing heterocyclic compound is part of the amino acid tryptophan? So you should link indole and tryptophan. So we talked about pyridine. That was the one I just drew with the nitrogen. These are referred to as azabenzenes. And I think what you should know about them, there's a variety of them, and they're readily synthesized. on the other hand, and there isn't even a picture for this, but I'm not sure how to say that. Ppyridine, also found in nature, but unlike our azabenzenes, it's really difficult to make these in the laboratory. Alkaloids have a bitter taste. The reason that they're in this chapter, they're also heterocyclic, they also contain nitrogen. And then finally, another fun fact about pyridine. And we can look in his notes to see if there's additional information. But we have this haunch, don't know how to say it, pyridine synthesis. Really readily makes a lot of pyridine. It's referred to as a super green reaction, which typically means that there's not really much waste involved, and it's you're not really getting any negative byproducts. But in terms of fun facts, those tend to sometimes show up on quizzes. So
I think he talked a lot about the Hansch reaction, but I don't actually know what it is.
yeah, so I had a feeling we're probably gonna have to go through his notes for that one. So let me pull those up.
One slide about